So, yes, welcome everyone. It's my pleasure today to introduce you Professor Anna Karczemska from the Lodz University in Poland. I would like to say some words about your professional trajectory. So Anna has really a multidisciplinary background, spanning from physics, material science, and also biomedical engineering. She has done she's degree in solid state physics first from the Lodz University, and then did a master in France in ECAM École in Lyon in France, and later she obtained a PhD following a doctorate in the Imperial College in London. Since 2000, she has been a faculty member of the Lodz University, where she is leading different research projects. Her research actually focus in one of the lines that she's working, focus on carbon-based materials, and particularly diamond and other carbon allotropes, as you have seen in the title of the talk. And she works from nanomaterials to also microfluidics and the applications in biomedical engineering. She's also very active. I think it's interesting also this part of her profile. She's very involved in science communication and academic services, contributing to very nice initiatives that promote the inclusion and equality to higher education. Today, she will share with us the insights in this fascinating world of carbon nanomaterials and the emerging applications in biomedicine. So welcome, Anna, and the floor is yours.
Thank you for inviting me, Imma. I'm very happy to be here with you. I have two aims. One aim is to share with you my fascination of diamonds and carbon material. You know, I'm a woman, so I love diamonds. But other carbon materials are wonderful too. But second thing, I want to share with you just what we are doing, what we were doing some time ago, some projects we dropped, some ideas we can continue. So I hope maybe we can continue somehow, maybe with your participation. Maybe also third aim, because I see many young people here, PhD students, I think. So maybe somebody from you would like to visit us in Lodz University of Technology. So you are welcomed if somebody would like to come to Poland for some time. It's great. From my experience, from my life, I can see that it's so important to visit other universities to look how the other scientists work in the other countries. So if somebody will be interested, contact me or just stay after my talk. Okay, so this beautiful creature is, life is based on carbon. So this picture is because of that. So allotropic forms of carbon, from physics and material science to applications in biomedical engineering. They are many applications. I can't say like that amount. I shared with Imma this year is 36th diamond, big, huge diamond conference. It will be somewhere in Spain. I don't remember where, but they are hundreds of thousands of different articles about applications of diamond materials, carbon materials in biomedical engineering. So what I will say is only very small amounts. This is biggest diamond in the world, Cullinan, which was cut to beautiful brilliants, which are in Tower of London. You can see them in Tower of London. I've seen them some time ago. But first of all, I would like to introduce you where we are from. I'm here with my colleague, Dr. Dariusz Witkowski. We are from Institute of Turbomachinery. So this is our building. and these beautiful Polish flowers. We are, which is in center of Poland, so it's very student city, we can say. We have many universities and music academy and art academy, medical as well. And this is part of our campus, so we are post-industrial campus. So on the right side, you can see these post-industrial buildings. In the 19th century, we had big textile industry development in our city. And also it's city of four cultures, so Germans, Russians, Jewish and Polish lived together up to the Second World War. On the left side is the old rector house, rector office, which was the palace of one of owner of the textile factory. So beginning, let's begin from the beginning. So, so 13.878 billion years ago, it was Big Bang. So how carbon was created? No, not in Big Bang. After Big Bang, there were quarks and leptons and this soup of quarks. And then hydrogen, first element, appeared. But carbon, it's later history. So stars had to be formed before. So all carbon atoms in our body, what we have, you can imagine now, are formed in stars. So we are children of the stars, which is fascinating to think. Another thing fascinating for me as physicist is that these carbon atoms are almost empty. Yes, so this nuclei inside, protons, neutrons made of quarks. Each proton, each neutron is made of 3 quarks, and electrons somewhere. So almost all atoms are empty. So if we see beautiful diamond, it's also, we can say, empty. And it's very interesting how the carbon atoms are formed in stars, because this process, this is triple alpha process. So from helium to 2 helium atoms collide, and if they have enough energy, they form nucleus of beryllium. But it's very low probability that it will survive. It's very small amount time, 10 to minus 16 seconds. So it's very low probability that carbon atom will be formed, but they are formed, and in bigger amounts that it's possible, like physicists thought in the beginning. So it's because the nuclear resonance of carbon increases the rate of carbon production in stellar interior. So it's kind of mystery, if we think about it, that carbon is formed in stars in such big amounts, so that life exists. It's something very beautiful, I think. And what is even, I don't know, more beautiful, it's the same beautiful, that this carbon atom, this carbon element, which is so popular in the universe, it's so popular on Earth, it can be formed, so many different materials can be formed of carbon. so many different materials. So we can have different, so for instance, diamond and graphite, this is the same carbon element. But because of different connections, different bonds between atoms, they have so extremely different properties. So diamond is so hard material with very special optical properties and with the highest thermal conductivity. So very often students don't know that diamond has higher thermal conductivity, 5 times higher than copper. So it doesn't conduct current, but it conducts heat very well. So they could be used for heat sinks in electronics, for instance. It's 2000 watt per meter Kelvin. So diamond as material has very extreme properties. Also for biomedical engineering, it's biocompatible. Diamond as material is chemically inert. We learn it at school. But I will tell later about nanodiamonds. Nanodiamonds are not chemically inert. They are bioactive. For instance, they stop different toxic reactions. If you mix them in blood plasma, very special. So if we introduce allotropic of carbon, we need to think to say about hybridization, and there are 3 possibilities: sp, sp2, and sp3 hybridization. So diamond is sp3 hybridization. It's the way how orbitals of atoms mix. So, and about bonds which carbon atoms connect to each other. And because of this hybridization, we obtain so different materials. But first of all, we have sp hybridization and very also mysterious material, carbine. They are 2 idealized forms, so polyene and cumulene, so single triple bond. So it's just such material, but I think it could be future because it's not well investigated. It's difficult to obtain it in stable form, but it should have very special extreme properties as well. So probably carbine is future. Graphite, so all of us know graphite, it conducts current. It's not so hard as diamond. And diamond, so each carbon atom is connected to 4 other carbon atoms with strong bond. And this hybridization, sigma sp3, which is important in this material. But this is not all. So we have 3 kinds of hybridization, sp, sp2, and sp3, but many other forms of carbon. And this is something fascinating. For the last 3 decades, there were several Nobel Prizes about allotropic forms, focused on allotropic forms of carbon, such as fullerenes. So Professor Kroto with other researchers. Graphene, everybody know this. This is just one layer of graphite we can say, with also very interesting properties. But we have many more different materials and possibilities of materials. So it's for me, it's very fascinating that so common material as carbon, but still it has future of investigation, and it is investigated, and it has a lot of applications also in biomedical engineering. Nanotubes. So nanotubes is sp2 hybridization, so that graphene is just rolled in the tube. Fullerene C60. So there are many other possibilities of other fullerenes bigger than 60 atoms formed in the ball. So even there are fullerenes who look like Mickey Mouse with ears. Also many applications in biomedical engineering. But they are mixtures of these different forms of carbon. As example, it's mixture of sp2 and sp3 hybridization. So like in graphite and like in diamond, and it's called novamine. So there are possibilities to manufacture also in laboratories different kinds of carbon materials for different applications with different properties. So we can somehow modify properties or obtain materials with specific properties which we want. These are beautiful diamonds from Vienna Museum in Kimberley. So they are natural earth diamonds, probably from South Africa. Yes, from South Africa. But for in 20th century, scientists try to manufacture diamonds in laboratory. So they have managed to do that. So it's diamond synthesis in high pressure, high temperature. So something which is obvious for us that in, for instance, Earth mantle, diamond is formed in high pressure, high temperature. But not only. This is meteorite crater where it's in Arizona, Canyon Diablo. It's called Canyon Diablo, or Beringer crater. And this meteorite, during collision to Earth, graphite was changed to diamonds. So in these meteorites, we can find micrometer up to millimeter size diamonds formed, in collision, during collision in high pressure, high temperature. But you can see that synthesis of diamond can be obtained in this HPHT process, so high pressure, high temperature, but also here in low temperature and low pressure. And we do that in Lodz University of Technology in Material Science Institute. So it is group where in chemical vapor deposition process, CVD, plasma assisted CVD process, diamond coatings can be manufactured from methane. So methane is gas. It consists carbon and hydrogen. So in plasma, if we apply specific amount of energy, this carbon atom, so plasma is fourth state of how to say, you know, it's solid state, yes, liquids and gas and plasma. So plasma is where ions and electrons are separate and gas starts to shine. So in specific conditions, carbon atoms can bond to each other to form diamond. So this sp3 hybridization. So we can obtain diamond coatings on different materials in low pressure and low temperature, which is even French people, I have seen such article, obtained in that way diamonds from cognac, because cognac also consists carbon, but maybe it's waste of cognac. So this is again Canyon Diablo meteor crater and piece of meteorite with graphite nodula, and in this nodula are diamonds from space. And this is CVD diamond synthesis, so you can see this plasma in plasma reactor and special conditions under reduced pressure. It's very important also role of electrons in this process. And this is apparatus, so this is plasma reactor. So we can put here, for instance, medical screw for bone from IC316L medical steel, and we close reactor. We prepare vacuum inside, then gas methane flows inside in specific conditions, pressure, etc. We apply energy by radio frequency, and we can in few minutes obtain 1 micrometer nanocrystalline diamond coating on the surface of this medical screw. It is very important because, as we told in the beginning of this talk, we have carbon in our organisms, and many times we have allergies for metals like nickel, chromium. So such coating, such diamond coating, such carbon coating can protect us from these metal ions, which is very important sometimes. Sometimes people can't have metal implants in their body because of allergy, because of such problems. So these are examples of applications of diamond as coating for different medical implants. And we do that in Łódź for many years, for the last 3 decades. So in stomatology, also this is heart valve made of titanium alloy, also covered with nanocrystalline diamond coatings. This is first surgery where it was saved the leg of a patient because this patient couldn't accept medical steel implant, and he had many infections and his body just rejected implants. So doctor decided to cut his leg, but it was final chance to have this coating, and his leg was saved. So it works. Also here we can see that diamond coatings, also nanocrystalline diamond, don't react with skin, so they are safe. also investigations are for years. And we have implementation of these nanocrystalline diamond coatings. So one Polish company also for years using these coatings for their products and sells this product. So this is example of applications, also endoprothesis coated with nanocrystalline diamond. Again, artificial heart valve. We can obtain different kinds of carbon coating. So I told before about nanocrystalline diamond. It means it's very thin coating, but it consists of nanocrystals of the sizes of tens of nanometers. So that's nano. And it is almost pure diamond, but almost. If it would be pure diamond, it would break easily. But because if it has some sp2 phases, it's better, so it doesn't break. It has better mechanical properties. Also, it has very good adhesion to the surface. But we can also obtain diamond-like carbon coatings, which are amorphous coatings. So especially it depends on application. Sometimes it is better. You can also incorporate some other elements to the coating. So dependently what you need, you can obtain even the increased antibacterial properties of the coating, for instance. So DLC coating is about 60% of diamond, 30% of graphite, maybe some carbines or other allotropic forms of carbon. NCD is almost diamond, but with some additions of other forms of carbon as well. So some it's interesting from physics point of view also how the carbons are formed, because we observe something in laboratory, but I'm also fascinating in diamonds in the space, in the universe. So nanodiamonds were discovered by astrophysicists in the space, just around stars. So maybe similar processes occur around stars, in plasma of the stars, and in laboratory in CVD plasma reactor. So we can somehow connect these processes from the laboratory and in nature. So not only in Earth mantle, but in different places of the space. Again, it's possible also to obtain thick diamond coatings. And scientists and different companies are better and better in that. So for now, we even have monocrystal diamonds, which we can use for rings, which are so for jubilers, so something for us women, with different beautiful colors. I've seen some diamonds like that on Diamond Conference, but it is important not only for beauty, but for some scientific applications and some technologies. For instance, because of this highest known thermal conductivity and some other applications. So it's very interesting to obtain such material, which you see, you can take it to your hand. It's millimeter thick or 2 millimeters thick. On Diamond Conference, I have seen also bigger, just glasses like 50 centimeters big and 2 millimeters thick. But this is polycrystalline diamond. So it is also makes difference because monocrystal always has a bit different properties than polycrystalline material. But even though this polycrystalline diamond has extreme properties and you can apply it for different applications, also biomedical. This is apparatus for obtaining such material. So in beginning of maybe 20 years ago or something like that, we collaborated with Professor Viktor Ralchenko from Russia, from Moscow. Now it's not possible, but okay, Russians were good in this technology. Also, a lot of Russians of Jewish origin came to different countries, and they opened companies selling diamonds. For instance, detonation nanodiamonds. One company is in Jerusalem in Israel, second is somewhere in USA. So these are people coming from USSR abroad. So they begin with these technologies. They are different diamonds. You have seen several slides before. This good optical property diamond. This is good for other applications. This is probably with addition of nitrogen, so it's not so transparent, but for many applications is interesting. This is example of surface morphology of this polycrystalline diamond material. So crystals are of the sizes of micrometers, which makes the properties of this plate very good. So it has very high, for instance, thermal conductivity. This is polished surface of diamond. But some years ago we had, so for my PhD, it was part of my thesis to apply diamonds for microfluidic devices, so lab on a chip, to sequence DNA, for instance, inside, because it has so high thermal conductivity. Joule heating will dissipate easier from diamond, so it could be used for extreme needs, for instance, for also high pressure, high temperature. When I was preparing to this talk, I found projects about lab on a chip, diamond lab on a chip, which they show sapphire and diamond or diamond lab on a chip when they use it for very extreme properties, so high pressure, high temperature. This is method, replica method. So we used opposite shape geometry in silicon, and we coated then this with diamond. It takes about 2 weeks to have coating of 1 millimeter, so this polycrystalline diamond, and then you can etch all silicon, and you have structures in diamond, because diamond is very difficult to shape. So you can do it such method or with special kinds of lasers, but it's also difficult. But this microfluidics maybe is also future idea for special purposes. So this is part of the chamber. These are examples of microstructures prepared with laser on polycrystalline diamond, and some showing some geometries of the channels. Also, what is interesting, by using laser to prepare microstructures on surface of polycrystalline diamond, you somehow can modify this material. So you can use such parameters that to not change diamond, but you can change diamond, for instance, to graphite, or modify it to amorphous material by using specific properties, specific parameters of laser. So it's also important because diamond is semiconductor, doesn't conduct current, but you can create just structures which will conduct current, for instance. So you can modify this material with laser as well. So we show it here. So here is not modified diamond, it's Raman spectroscopy spectra, 1333 peak. It indicates diamond presence and these sp3 bondings. But for instance, such shape indicates more amorphous material. So it's proof that we can modify as we want diamond surface. Other projects we had with Dariusz, a very interesting project when we were very interested in antibacterial properties of nanodiamonds. So as I told some minutes ago, diamond is chemically inert, but nanodiamonds, because they are of sizes of few nanometers, 3-5 nanometers, they have huge rate of surface to volume. So this surface chemistry is very important in nanodiamonds. So you can modify this surface chemistry of nanodiamonds by specific chemical reactions or by physical methods, different methods. And you can obtain material, nanomaterial, with for specific applications. For instance, you can increase antibacterial properties of nanodiamonds. So we try to use these nanodiamonds. We applied for two patents in December last year after this project. So we have this technology. And we can also use it for different purposes. So we had idea to use it for antimicrobial coatings, for instance, for the places which we touch. These are nanodiamonds, so box of nanodiamonds. It doesn't look very spectacular, but these nanodiamonds are of the sizes 3-5 nanometers, but they join together in bigger conglomerates. So it's also very important to prepare this material, also clean this material, because very often these detonation nanodiamonds, the core is sp3 diamond, but on surface it's like onion, and it has some graphite or some impurities. So, but it's very special material. You can do a lot of things in it. And here is just idea that you can modify surface of nanodiamonds in different ways. You can find many scientific articles on the topic for many different applications. This is idea of our project. Also, we proved that nanodiamonds are safe. So we collaborate with many groups in our university, also with colleagues from chemistry department, different groups from chemistry department. One group is focused on biomaterials. They have lab with biological lab and also with bacteria, and they did some investigations of cytotoxicity and some other research. Also, we had another project, and we mixed nanodiamonds with fish tropocollagen for applications for wound healing. So also we used these antibacterial properties of nanodiamonds, and we prepared lyophilizates of this tropocollagen mixed with nanodiamonds. Nanomaterials are future, so we work with nanomaterials. This is, I love Richard Feynman. He was first who thought about nano machines, nanomaterials. In 1959, he gave talk about it. But we live in the epoch of nanomaterials, nanotechnologies. So nanodiamonds is part of this. Also, what I love and what I'm fascinated in are space diamonds. So we also investigated. It's my scientific hobby. So I investigate also carbon materials in meteorites. So we obtained just very, very tiny amount of dust, diamond dust, nanodiamonds dust, and these are presolar nanodiamonds. So scientists from Mainz, Professor Ulrich Ott, wonderful man, sent us some sample. Their scientists just dissolved all the meteorite with a long process, and what left was this amount of nanodiamonds. And this is such nanodiamond. It's about 3 nanometers big, so it's the size of diameter of DNA, about, like we can imagine. It's difficult to imagine these sizes. And we tried and we succeeded to do Raman spectroscopy of these presolar nanodiamonds. Why presolar? Because in some primitive meteorites, some grains stayed after formation of solar system, so they were formed before our solar system was formed. So we can touch such material. So we can imagine a beautiful universe, and I'm sure lots of nanodiamonds, fullerenes, graphene already were discovered by astrophysicists somewhere in some places of the universe. Cosmochemistry is very, very interesting, and in how many different regions are formed in space. Also, some articles like this one from 2011, formation of fullerenes and also graphene. So it was discovered in space. It's you've seen this, and these are samples of meteorites. These meteorites are called uralites, and they have carbon veins. So they are built of olivines, pyroxenes, different minerals like that. But between they have carbon veins of sizes of few millimeters or micrometers. So this is such vein, and all the dots you can see which are outside are diamonds. So these diamonds are of the sizes of 20, 80 micrometers, something like that. This is Raman spectroscopy of presolar nanodiamonds, which we obtained. These are meteorites from Vienna Museum, and me between them, very happy. And with Saint Ignatius Loyola. We are looking for life in the space as well. It was famous meteorite and article from 1996 where they found something like that, like bacteria or it's Mars meteorite. But of course, it's not proof that it's life. We haven't found life anywhere. For instance, we have found bricks of life in meteorites. Also, there were some missions like on Bennu or comets where nanodiamonds were found, different allotropic form of carbon or different carbon materials, even nucleotides were found in meteorites. So some organic chemistry is happening in our solar system, and different places where maybe life can be formed. And this primitive meteorite, this is example, this Orgyle meteorite, is known for having extraordinarily primitive composition, and also it consists nanodiamonds and different carbon materials, and some other so all these dots you can see in this vein, which are outside, are just beautiful cosmic diamonds. And everything what shines here, it's a cathodoluminescence picture. So they shine in different colors, golden, pink. So what is fascinating in these diamonds from meteorites is that each is different because of the defects. So you can find there probably many different carbon materials and many different kinds of diamonds which differ from each other. So here is diamond, here is diamond. Beautiful. For me, this is beautiful. And this is proof. So each diamond shines in cathodoluminescence. This is beautiful diamond. But for bacteria, it's diamond for bacteria size. And future belongs to you young people, young scientists. So if you are interested in carbon materials, maybe you can investigate something. Some years ago, I found article about presolar nanodiamonds, and I was fascinated with this, and with some other properties of diamonds for biomedical engineering. So maybe you can find something which you will find interesting for you. Also, if you are welcomed to Lodz University of Technology. Lodz is city of students, so you can find many interesting things for you. We have doctoral school in our university. Probably we can find place for you if you are interested. We have different faculties. We are from Faculty of Mechanical Engineering, but we have friends in many other faculties. So if somebody will be interested, we can help you in maybe finding opportunity to visit us. Okay, thank you for your attention.
So thank you very much, Anna, for this introduction about the nanodiamond wall, and also to explain us about your expertise in meteorites and space science also, that I know that it fascinates you. So thank you very much. So I'm sure there are some questions or curiosities for Anna.
Hello, Anna. Nice presentation. I just wonder when you compare the nanographite or nano diamonds, sorry, with the boron nitride, because boron nitride is, I think, the most used, very extended coating for in industry, I think. How can you compare both of them?
I didn't work a lot with boron nitride, but what I can prove from the decades of research is that what I said, that because we have carbon in body, carbon diamond coatings, nanocrystalline diamond are biocompatible, or nanodiamonds are biocompatible. So that's interesting for biomedical engineering applications. So one thing which can be compared is, I think, that diamond is carbon, so it's safe for us. And second thing is that we can prepare very different materials of very different properties. So I think carbon is very special because of that, because we can modify properties, we can prepare many different materials from the same element for different applications with different properties.
I'm curious to know more about the antibacterial coatings that you mentioned. I mean, you mentioned that the coatings that you made with nanodiamonds, if I understood correctly, were able to kill bacteria, but they are not, they are safe for humans. So what's the reason? Because they are able to, to kill the bacteria and they are not doing anything, no harm to our human cells.
You know, it all depends how you modify surface of nanodiamonds. So, for instance, one of patents which we have, because dependently what you attach to surface, you can obtain different properties. So, for instance, we attached ciprofloxacin, so this is antibacterial reagent, so that's why we increased antibacterial properties. But they are, but we also our friends from chemistry department proved cytotoxicity level that is very low, but how I feel that and how I understand that we still know very little about nano risk. So risk of these nano materials that we of course investigate it, but we should go deeper to that from different perspectives in different methods, because I think this is crucial. And yes, I can find in literature most of articles that nanodiamonds are safe, but dependently how you prepare surface, you can increase toxicity as well. So all depends.
Is there some other question? There, and then you, Ellen.
I was wondering, like, when you do this coating of nanodiamonds, does it also improve the mechanical properties of the material? Like, I don't know, imagine you put a coating of these nanodiamonds on paper-like material or something like that. Is it also improving the mechanical properties?
it's two thin coatings. It's about 1 micrometer. So if you coat, for instance, screw from medical steel IC316L, mechanical properties are because of the screw has specific mechanical properties. So not much with mechanical properties. With friction, yes, you can modify friction, for instance, of surface.
Okay, thank you.
Maybe the last question.
Hello. First of all, thank you for your presentation. I enjoyed a lot. I was wondering, following his question, you said that you sometimes modify the surface of the nanodiamonds with antibiotics, but if you remove the antibiotics, I understood that the nanodiamonds have an antibacterial action by themselves. And if that's the case, do you know the mechanism? How do they attack bacteria exactly, like, or more or less?
So our experience is that only this modification by attaching some antibacterial reagent increases antibacterial properties of nanomaterial. But I found literature which says also that by themselves these nanodiamonds have specific antibacterial properties. You know, also graphene or nanotubes also can have, but graphene is more toxic, or nanotubes as well. So our experience is that attachment of these antibacterial reagents are important, but also I think it's important that, okay, nanodiamonds are of the sizes of 3-4 nanometers, but they are very keen to agglomerate. So it's very difficult to make them separate. So if you make them separate, they possess different properties as well. So probably because of that, we couldn't manage to make nanodiamonds themselves by antibacterial. But I found in literature that yes, they are.
So I guess the presence of the nanodiamond improves the antibacterial effect of the antibiotic by itself. Otherwise, no?
Could be, yes. But I think more investigations are needed, especially from our side.
Okay, so I don't know if I think that we can thank you, Anna, for this talk. Thank you very much. And Darius and Anna are here the whole week. So if someone is interested to contact them, just let me know and I can put you in contact with them. They are in the campus actually at the Autonoma University. So, but they will be around. So thank you, Anna, very much for this talk.
Thank you. You can also send me email if you will want to contact us, and Imma has contact to me. So we are open, Darius as well. You can contact me or Darius, and you are welcome in Poland.
Okay, thank you. Thank you very much, Anna. Thank you.